Hello everyone. So in this session we'll see a lot about power. We'll see the methodology. We'll see how we can analyze power. So the agenda is I'll introduce the tool called Power Compiler. Power Compiler is part of the Synopsys Design Compiler suite. It is used to it's just you can say that it's just a set of features inside design available inside Design Compiler, which lets you work on the power. Then we'll see the design flow, Power Compiler design flow. We'll see how it fits into the Synopsys synthesis flow. Then third, we'll see how the power is modeled, what kind of different power numbers would we be interested in, and how they are calculated. We'll learn about switching activity. SAIF is a file format that is used to pass on that information, the switching activity information. We'll see what is switching activity, how is it used. We'll see how do we analyze power numbers, how do we go through the reports. Then we'll see a very interesting implementation, and perhaps the most useful for single voltage design, the Power Compiler clock gating. And lastly, we'll see how power is optimized in design. So let's start with the introduction. So Power Compiler is part of the Synopsys Design Compiler family, synthesis family. It is used to perform both RTL level and gate level power optimization and gate level power analysis. Why the power analysis cannot be performed on RTL, it will become very clear. RTL in the later slides also, but let me explain it here itself. In RTL it does not have gates, right? RTL has Verilog, for example, Verilog RTL has always got declaration of wire, but it does not actually have gates. And there is no concept of reporting power on RTL. You can actually analyze RTL to reduce power. You can employ some techniques in RTL itself to reduce power, but what actually is the power number you cannot know, because power numbers are gate and technology dependent. So you need a netlist to know the power number, and that netlist should be mapped onto one of the technology libraries, which will contain the power numbers. Right? So logically, you could optimize power on RTL, but you can do power analysis only on gate level. So Power Compilers, various power, there are a lot of power reduction techniques in Power Compiler, most famous being clock gating. There is something called operand isolation, multi-VT leakage power optimization is a very important thing, but it's a very useful thing that is prevalent in a lot of designs. And gate level power optimization, again there are some techniques. So there are some techniques which are very useful, very used extensively for single voltage design, which we will see. Few of the techniques we will see. Then there are a lot of advanced techniques which are used for multi-voltage design. That means a chip will have different voltages for different sections of the chip. We won't go into that because there is a separate methodology for that, separate ways of implementing that, but that's outside the scope of this course. So we will be focusing on the power optimization and power analysis of the single voltage design and what techniques do we employ. So the methodology so power is usually of two types. We divide the power into two types: leakage or static power and dynamic power. So the methodology involves how do we we analyze the leakage power, and Power Compiler helps us to reduce the leakage power by using multi-VT threshold power optimization and power switching. So each of these terms, what I am discussing here, we will see details of it in the later slides, in the upcoming slides. Then there is something called dynamic power optimization, which uses the ways are by inserting clock gating cells. There are a lot of options available when we insert clock gating. Operand isolation, gate level power optimization. Then we can do RTL level power optimization, again inserting clock gating on that. We can do gate level power optimization by using multi-VT threshold voltages. Dynamic power optimization can be done by reading the switching activity. Again, power compiler gives us ways to analyze power in both RTL and gate level using simulation data as well. So don't worry if some of these terms are not clear; they will become clear as we go. So the design flow is pretty simple. In fact, design flow at both RTL and gate level stage is same. There is the analysis part. The simulation is very important when we talk about power numbers, because let's say I have a design, I have an FSM, and I would write. So the design cycle would be like this: we would design the FSM, and we would design a test bench that will test the FSM. There will be a mission mode test bench that will take this FSM through a number of test cases which mimic the real world function, right? Which will mimic the real world scenario. So we will exercise FSM, we will give inputs in such a way that those inputs, the similar inputs, are expected to be given to FSM in real world application. So this stimulus will actually determine how much power that FSM would take. Simulation is a very important part of power analysis. So because simulation gives us something called switching activity, we'll again see the details of it later. So simulation provides us a switching activity. So we can use the switching activity for analyzing. Plus, power compiler can use the switching activity to also optimize the power. So at both RTL level and gate level. So this is the optimization flow. It's very similar to a regular design compiler optimization flow. The only thing extra is power. Technology library and RTL design are staples here. We will need that definitely. We have to just enable power optimization. We will see how we can do that. Then we do synthesis and power optimization. So see, simulation here is feeding this SAS file. So this is called switching activity file. It goes as an input before the synthesis takes place. So now synthesis has what it has. It has technology library. It knows the power number. It has the switching activity. So it knows. We will see what information does the switching activity provide. And now it can do the power. It can do power optimization. Then you can use some reporting to report power. Then we get a gate level power optimized netlist, right? But there's one more option is that so this simulation is taking a place at the RTL. We can again simulate this. We can apply the same stimulus to the netlist as well, and we can also get the so after the design is routed, we also get the capacitance information. We can feed back this information and do further accurate power analysis. Now let's talk about the basics of power. What are the power terminologies we use? What are the power? How do we calculate power numbers? So power is drawn from the voltage source that is attached to the VDD of the chip. So it is very clear from the first instance that the higher the VDD, the higher the power number. So P is equal to I into V. V is nothing but VDD here, the current drawn from the power supply. This is the reason that most of the now as the technology shrinks, as we move on to nanometer scale, the sub-deep submicron, the VDD is reducing. So earlier in 90 nanometer odd, 130 or 180 nanometer odd, the VDD went up to 1.2, 1.5 volt. But now we are in the range of 1 volt, 0.9 volt. So as we decrease VDD, obviously the power is decreasing. So for example, handheld applications like mobile phone, the chips will not, hardly there will be any chip which will require more than 1 volt for digital portion, right? So instantaneous power is IDD dependent on time into VDD. VDD is fixed. Energy is again integral of power dt. So integral of power with respect to time. So we substitute the values of I and V. Average power is energy divided by time. So it's 1 by T. We just substitute the value of energy here. So this is the average power number. Now we use this equation to calculate all other power numbers. Now the power numbers are divided into two types: static power and dynamic power. Again, dynamic power is further divided into two types: switching power and internal power. We'll see what each of these means. Static power is consumed even when the chip is switching. That means even if no activity is taking place in the chip, it consumes a bit of power. This is called standby power. Let's say, for example, your mobile phone. In fact, mobile phone works. In fact, mobile phone, even when you're not doing anything, it is the smartphones do a lot of tasks in the background. But let's talk about the feature phones, which do not run so many tasks in the background. Even if you are not doing anything, you're not talking to anybody, you're not listening to any radio, the chip consumes power, right? So this is called static power. That means even when the chip is in quiescent condition. What is the largest? You already know by experience that the standby time for feature phones is much longer. It runs into like 5 days, 10 days, or so on. So it is understood that static power is the lesser culprit here, but the largest percentage of static power results from source to drain successful leakage. And with the shrinking technology, so it depends on the single most important factor here is the VT, that is the threshold voltage of the device. So with shrinking technology, with VDD going lower, the VT is also going lower. VT, these are the equations for the drain to source current, the threshold leakage current, and as we reduce VT, this current increases. What it means is that as the technology shrinks, the leakage power contribution is increasing. For example, 45 nanometer cells will be more leaky than the 90 nanometer cells because the VT would be lower. You can verify from this. So this is the VT formula: VT naught minus theta VDS plus gamma. This is the this part here. This part of the equation here is related to the effect of the bias voltage. So usually if you go back to the equations of PMOS and NMOS, the transistor equations, you would see that usually at the start of the understanding, we assume that VSB is 0, the body effect is 0, but you could have a case where the body voltage is not 0. So there will be some difference between the voltage at source and voltage at body. So this takes care of that effect. This takes care of the drain to source. This depends on the drain to source voltage. So VT, the lower the VT, so the principle is that the bottom line is the lower the VT, the more leaky is the device. Why? The lower the VT, the higher is the IDS, and therefore the lower the VT, the more leaky is the device, but the device is faster. So what it means is that the technology library guys who build the technology library now have options, right? They can either build a device which is fast, but then by playing with the VT, but then device is also faster, but it consumes more power, it consumes more leakage power. Again, you can raise the VT and make the device slower, but then it will be good for low power applications. So we'll see more of this in the coming slides. How is this useful for us? So again, I stress that static power in present day, static power is, or we use the term leakage power, is caused due to sub-threshold source to drain sub-threshold leakage. This is the leakage power is the majority component in the static power. Right? Now comes the dynamic power. Dynamic power, two types: switching and internal. What is the switching power? So dynamic power is required to charge and discharge load capacitances when the transistor switch. So for example, looking at the inverter, we see that inverter during the operation it switches from 1 to 0 or 0 to 1. So one cycle involves a rising and a falling output. On rising output, the node C gets charged up to VDD. So charge Q is equal to CVDD is required. When the output falls, the same charge is dumped to ground. If we take a time period of t and the switching frequency to be FSW, so by t times FSW, it gets repeated, right? The charging and discharging of the load. Let's see how dynamic power is calculated. So again, we take the same equation, 1 by t IDD VDD dt. The t is kind of a constant here. It comes out. Again, we rearrange the equation. We multiply it by PFSW. So you could say that 1 by t is nothing but FSW, and integral of IDT comes out to be CVDD. So the equation now here, this is the final equation to be remembered. CVDD square FSW. Right. Now, so what does the dynamic power depend on? Dynamic power majorly depends on obviously the VDD. If VDD is lower, the dynamic power is lower. It depends on the load capacitance. The higher the load capacitance, the higher the power. And this is the most important thing, FSW. This is the switching activity. More frequent a signal switches, the more frequent the gate switches, more is the power. Right. So signals. What is the signal that switches more frequently? It's the clock. What is the signal? So the switching frequency of the clock is highest. It toggles like twice per cycle. It goes to high, goes low. Again, the higher frequency clocks will have more switching activity compared to lower frequency clocks per unit of time. So high frequency clocks, that is why clock networks, high frequency clock networks consume most of the dynamic power. Right? Data signals comparatively switch lower. The switching frequency of data signal is not as high as clock. So let's say the system clock frequency is there. Let the switching FSW is equal to alpha f, where alpha is the activity factor. Now, if the signal is a clock, alpha is equal to 1. What it means is that if the signal switches twice per cycle, alpha is equal to 1. If the signal switches once per cycle, alpha is equal to 1 by 2. Please remember this. Dynamic gates switch either 0 or 2 times per cycle, so average alpha we take to be 1 by 2. Since when a signal switches once per cycle, alpha is equal to 1 by 2. Signal switches twice per cycle like clock, alpha is equal to 1. For dynamic gates, they either switch 0 or 2 times. If they switch 2 times, alpha is equal to 1. Alpha is equal to 0 here, average alpha is 1 by 2. Static gates depend on the design, but typically default values have been seen to be alpha is equal to 0.1. This is only for data signals, not for clock. For clock, it's special case, alpha is equal to 1, right? Data signals, they typically switch less, so alpha is just a number based on some statistics. So now the dynamic power equation becomes alpha CVDD square F. So we replace FSW by alpha F. F is the clock frequency now. What happens to data signals? For data signals, we would be concerned about the clock they are related to. For example, we write in always block, always at posit CK. We capture some data on that clock. Now that data will actually the meaningful clock is the same clock it's capturing the data on, not any other clock. Let's say your design has multiple clocks. So each data signal will have a relative clock, right? The frequency of that clock should be taken into consideration. So let's say a data signal working on 100 MHz. You have, let's say, 2 clocks in your design, 100 MHz and 200 MHz. Not all data signals will work on 200 MHz. Some of the data signals will work on 100 MHz, some of the data signals will work on 200 MHz. Right? So this is why the data is also associated with the clock frequency. Second type of power, dynamic power, is internal power. When transistors switch, both NMOS and PMOS networks are momentarily on at once. This leads to a blip of short circuit current. So whenever there's switching involved, so let's say for an inverter, let's go back to an inverter. Whenever there's a switching involved, so let's say NMOS is turned on, PMOS is off in static condition. Output is 0 because NMOS is on. when the input changes state, NMOS starts going from on to off condition, PMOS starts going from off to on condition. Now there is a overlap of time during which both NMOS and PMOS are on. This leads to a burst of short circuit current. This short circuit current, although is less for one device, but consider thousands of or hundreds of thousands of devices in a chip switching state, right? So for a big chip, this becomes significant. This kind of short circuit power becomes significant. If the rise fall times are comparable for input and output, and for faster frequency time, typically this would be less than 10% of dynamic power. So still, the internal power is less prominent than the power that is based on switching activity, which is the switching power, right? So dynamic power. So in terms of in present day chips, the most important factor is dynamic power, which is caused by switching. That means charging and discharging of load capacitor. Second is dynamic power, which is internal, the short circuit power. The third is the leakage power, that is dependent on the substation leakage, right? So these are the three major power factors. So internal power is again. So internal power is a more generic term. Short circuit power is type of an internal power. So internal power, by definition, is any power that is dissipated within the boundary of the cell, inside the cell, not dependent on the load capacitance, right? During switching, circuit dissipates power by charging, or so in fact a complex gate will have lot of source and drain capacitance which is inside that gate, not counting the outside load capacitance, right, connected to the output. So all these capacitances, internal caps, are charged and discharged during switching. So this also counts as internal power. For circuits, now internal power depends a lot on the transition times. If the transition times are faster, the overlap window during which P network and N network are simultaneously on is shortened. But for slower transition times, you can actually draw the diagram and see. For slower transition times, this time expands. The overlap time expands. So if you have slow transition times, it can even consume up to 30% of the total power dissipated by the, which is very, very significant. This is why faster transition times are good for everything. Faster transition time means the delay is faster because the output delay depends on the output cap and input transition time. So faster input transition times means good delay, and they also mean less internal power, right? So the short circuit power, as I told before, short circuit power is the majority component here for internal power. But for more complex cells, the charging and discharging of internal capacitance might also be the dominant source of internal power. Right? So this is an illustration for an inverter. ISC is the leakage current. ISC is the short circuit current. ILK is the leakage current. Leakage current is the subthreshold drain to source leakage. Short circuit current only happens during the switching, and again there is the load capacitor. So ISW is the switching current. So there are three currents responsible for three separate power numbers. Switching current, again I'll repeat again. Switching current SW, which charges and discharges the load capacitance, is responsible for dynamic power switching. Short circuit current is responsible for dynamic power internal. It is caused when P and N are simultaneously on during switching for a short period of time. Leakage current doesn't depend on switching. Leakage current is the current that goes from drain to source during the subthreshold case. That means so it depends highly on VT. If VT is lower, subthreshold leakage is higher. If VT is higher, subthreshold leakage is lower. It is also called leakage power. That's why it's called leakage power or static power. So static power and leakage power are interchangeable terms. So dynamic power, you need to be sure what type of power it is, either it's switching power or internal power. Again, the name suggests static power doesn't depend on switching. Dynamic power depends on switching. Dynamic depends on switching. Static does not depend on switching. Static is the quiescent case. This the case where the chip is not showing any activity. Now, let's see how does power compiler calculate leakage power. Now, leakage power is pretty simple. Does not depend on any switching. So, what power compiler needs to do? Power compiler needs for each cell. Power compiler just needs to read the number from the. So what you can do is at this point of time, and after this again, you can go back, open your standard cell library, and see that every cell, start with a combination cell. Every cell will have some power number. One of those power numbers is designated as cell leakage power. So that is the leakage power of that device, of that cell. For each such cell in your design, now let's say your design has 10,000 gates combined, combination and sequential combined together. For each of those 10,000 gates, the power compiler just needs to go to the library, grab the cell leakage power number, and that is the total leakage power of your design. So P leakage total is nothing but summation of leakage power of each cell. Right? So libraries provide single leakage power. They can provide single leakage power for all cells in the library by using the default cell leakage power attribute. So a very rudimentary, a very first cut library may have a default cell leakage power attribute. For this will apply to all the cells in the design, unless and until or if you want to go more specific, which is the case, because a 2-input AND gate will probably have less leakage than a 3-input NAND gate, for example. So multi-input gates will have like 3-input gates will have probably have more leakage than 2-input gates because the number of devices are higher in the letter. So so there is one default cell leakage power attribute in the library, and then there is a cell leakage power attribute library attribute which is per cell. So per cell leakage power is denoted by cell leakage power attribute. If this leakage power attribute is missing or negative, it cannot be negative. Tool assigns the value of the default. So if for a particular cell the tool does not find a cell leakage power attribute, it will look for default cell leakage power attribute. If it is not available, even the default number is not available, it does not have any choice but to give it 0. There is also something called a state dependent leakage. Now let's say for an AND gate, if you go into more specifics, the leakage power will be different for the 4 cases. What are the cases? The cases are the 2 inputs can be either 0, 0, 0, 1, 1, 0 or 1. So there are 4 states. So an AND gate will probably have different powers for each of those states. You can also have a state dependent cell leakage power in the library. You can open your library and see if there is any state dependent leakage. We'll probably see in the lab. We'll go into the library and see how the power numbers are represented in the library. So again, to calculate the cell leakage, so now what happens if there is a state dependent leakage, right? So if you do not give any other information to power compiler, it will assume that all the states are equally probable. So what it does is that it will take the average of all the states. Right? So to calculate cell leakage power, it determines the unit. First of all, it determines the unit based on the leakage power unit attribute. Then it checks for the leakage power attribute, the leakage value of. So for each state, the leakage power is multiplied by the percentage of total simulation time at that stage. Now, let's say you are able to tell power compiler that, for example, for an AND gate, you're able to tell power compiler that one of the states is more likely to happen than other states. This is called, again, this is nothing but switching activity, right? A form of switching activity where you are able to tell the tool that one of the states is more likely to happen than other 3 states. In that case, the leakage value of each state is multiplied by the percentage of total simulation time at that state and then sum. So it's a weighted average. Right? In case no data is available, it's just a simple average. So if the state is not defined, if you define the value of cell leakage power is used to, if a particular state is not defined, the value of the cell leakage power attribute is used to obtain the contribution. Let's see an example. So now this is a 2-input NAND gate. So the library will have something like this. It will have a leakage power unit, it will have a cell leakage power, and it will have a state dependent leakage power. Now here all the states are not given. Now let's say for the total time of 600, it can be any unit, nanosecond or picosecond, whatever, we are able to tell tool by some way that the state A into B, that means A and B both being 1, happens for 33% of the time. Rest of the 67% of the time is for other states, right? So what is the weighted average? Weighted average is 0.33 into 0.2, because 0.2 is the leakage power when the state is A and B, and we are telling the tool that 33% of the time this gate is in this state. So 0.33 into 0.2, and rest of the remaining time is 0.67 into the default value, that is the cell leakage power. Right? This way, the tool calculates the leakage power for a particular gate. So again, the priority is the state dependent leakage power. If that is absent, it will take the cell leakage power. If even cell leakage power is absent, it will look for the default cell leakage power attribute. So there are three attributes, right? Default cell leakage power, and the state dependent leakage power. Again, please note, leakage power does not depend on the switching. It although depends on the state of the signal. So for a state dependent leakage, if the state of A and B is 1, the power is different. If the state of A and B is something else, the power is different. Right? It can be state dependent, but not switching dependent. Now, a very important, I was stressing on the fact that leakage power depends on the VT, on the threshold voltage of the device. So you could have cells with low VT, but they are faster. You could have cells that are high VT, but they are slow. So static power dissipation has an exponential dependence. It's not even linear. So it has exponential dependence on the switching threshold of the transistor voltage. In order to address the needs of the low power IC design, the technology library providers provide cells with multiple threshold voltages. So now earlier we saw that, for example, there was 2-input NAND gate. Now the 2-input NAND gate will probably come in 2 or 3 threshold flavors, right? So what is popularly done nowadays is that there are now 3 threshold voltages for each cell. That means the 2-input NAND gate will be available in a low VT flavor, a standard VT flavor, and a high VT flavor. The high VT will be slowest and best suited for power. The standard VT will have a standard delay, that means between high and low VT. Power is also between high and low VT. The low VT would be fastest, but the least. Now, how do we as a designer use these cells, or how does Power Compiler as an EDA tool use these cells? So what is clear is that for all lower speed applications, or where the clock frequency is lower, or let's say the path is easier to meet, it's logical that we should use the high VT cell. Why? Because even if the cells are slower, since we are working on low frequency or a large timing path, the high VT should be able to meet the timing, but it will be consuming least leakage power, right? It makes sense. Again, for timing critical paths, you can incrementally try and replace high VT by standard VT. If the timing does not meet, you will probably go to low VT. So for a typical a big block, a typical cell distribution should look like this. The high VT would be about, I'd say, 80% of the cell would be high VT, because similar number of paths would be either easily met or low frequency one. About maybe 15 to 17% would be standard VT, and very few cells, maybe 3%, 5%, or even lower than that, even 1% would be low VT, because low VT would only be used in very highly timing critical paths, right? So what many people do is that they will say that okay, I'll only synthesize with high VT to achieve best power number. I'll only synthesize with high VT, and since the critical paths can change after synthesis, right? Synthesis does not have the accurate net information because the design has not been placed and routed, right? Since synthesis does not have the accurate the net numbers, the capacitance numbers, the accurate information is available only after placement route is done. So the critical paths can change after placement and routing. They do change. So what I can do, one methodology I can apply is that I synthesize with high VT, but I enable standard and low VT only after placement route optimization. What it does to my design is that my design is majorly high VT, and only let's say real critical paths only appear after routing. Only the real critical paths have either standard VT or low VT. What this gives me is a design that is optimized for power and optimized for time. Right? So there are again many ways by which you can achieve this. Whatever I discussed is just one of the ways which I have been using in this industry. Or we would see that power compiler, in fact, how does power compiler do the job? Right? Power compiler can automatically do the job for you. How does it does? Right? We'll see in the upcoming slides. So, but it is very clear that present day needs, present day technology library have cells of multiple VT, which support multiple VT, and you should use them, and the tool should use them to achieve good power numbers, right? So this was what we discussed in the last two slides was the power calculation for the static power, for the leakage power. Now let's look at the dynamic power or the internal power, right? Now when computing internal power, this power compiler. So first, for leakage power, the attribute was cell leakage power. For dynamic power, the attribute is called internal power. That's why I have written internal power. Right? Don't confuse it with the short circuit power. Now this here, the internal power is the attribute that libraries use to denote the dynamic power. Right? So when computing internal power, power analysis will use the information characterized in the logic library. So no, this is sorry. This internal power in fact refers to the short circuit power within the cell. We will see the dynamic power that is based on the switching of the output load capacitor in the separate slide. So this internal power in fact represents the switching power, but totally internal to the cell, right? Internal to the cell, but counting the capacitance that is implicitly built into the gate at the output, right? So the output is connected to the combined range, so that capacitance is also included here, right? Plus the short circuit current. So here the internal power refers to the power that is completely internal to a cell, which includes the short circuit power plus the internal capacitance, but not the load capacitance, extra load that is applied to not the fan out load, right? So when computing internal power, it uses the information characterized in the logic library. The attribute is called internal power. The internal power table is very similar to the timing table, cell rise, cell fall table. Again, for a non-linear, the most popular model is the non-linear delay format, non-linear delay model (NLDM). It is very similar to the timing table, right? So both have lookup table based, and both can be multi-dimensional. So in case it is one-dimensional, the constrained input is the input transition. If it's two-dimensional, it could be input transition and output load capacitance. It can also be three-dimensional. It is not popular though. Input transition, output load capacitance for two outputs that have equal and opposite logic values, like Q1 for a clock, right? Q or Q1. So this is a lookup table. So power is calculated on. There are two factors. One is the weighted average input transition time. Other is the output load capacitance. Here, the output load is the implicit load that is on the output of the gate, not the load presented by the nets, right? This is the internal power. So it's very similar to timing. You can open up the library and see the internal power attribute. Just like it computes timing, power compiler computes the power numbers for dynamic power internal case, right? Again, this is state and part dependent. Now, cells will often consume different amounts of internal power depending on which input conditions. Right? Now, let's say there's a complex cell in the lab. The inputs are A, B, C, and D. The output is Z. But now, when we go inside this standard cell, we see that there are 3 levels of logic. This is how it's built. Let's say, assume this is how it's built. Now, when the input A transitions, 3 AND gates are affected. But when input D transitions, only Z is affected. What it means is that this gate, the standard cell, has different power numbers for different cases. So again, this is state and part dependent. So power compiler will choose the appropriate part dependent internal power table for an output by checking the related pin attribute. So timing is also has a related pin attribute, power also has a related pin attribute. So what timing and power tables will look like for this cell? For pin Z, for related pin A, there will be a power table and a timing table. Again, for input B, there will be a power table and a timing table, right? Which will be different than A. Again, for D, it will be different than both A and B. So power compiler does not choose the worst power number. Now this is dependent on switching. Please note this kind of power is dependent on switching. Assume that power compiler knows how A and B, C and D are switching. So whenever D switches, it will take power with respect to D. When A switches, it will take power number from the table for which the related pin is A, right? And so on, right? So it's always state and part dependent. Now let's talk about the switching power. Switching power is the power that is consumed in charging and discharging the load capacitor. Now this is not the internal power, this is power that is due to the switching of the cell, but switching on and off of the load capacitor connected. So this load, what does this load come from? This load comes from the nets, right? Again, we understand that in design compiler the net information is estimated, it is not accurate. So this kind of power again is an estimate because the load itself is an estimate, right? So PC is equal to VDD square by 2, P load into TRI, which is the toggle rate. PC is the switching power of the design. Toggle rate is the toggle rate of the net I transitions per second. VDD is the supply voltage, right? So we saw that a signal that transitions for let's say once per cycle, the alpha value is 1 by 2. So we substitute the value of 1 by 2 here, and we substitute the switching by the toggle rate, which is transitions per second. So this formula is same as the earlier formula, not different. So remember, P is equal to VDD square by 2, summation of, so VDD is constant, summation of P load into the toggle rate. So each net load into how many times it toggles, we add them together, multiply by VDD square by 2. This is how we get the switching power, right? This can be either, if we are working at the pre-layout stage, that means we are working on a synthesis database, synthesis netlist, it will be an estimate. We can also use power compiler. We can read the capacitance information, the accurate capacitance information after the layout has been done. It is called a post-layout database. We can also do. This is the process called back annotation. When we read the capacitance from a separate file and apply it onto, so what netlist has? Netlist has information on the gate and the number of nets. So we can choose the post-layout netlist. But now, for each of those nets in the netlist, design compiler or power compiler also needs to know capacitance and resistance for each of those nets. This data comes from a separate file, which is called either SPEF. The most popular format is SPEF, SPEF. This process of reading the capacitance from a separate file is called back annotation. Right? We will see a lot of back annotation in unit file. If you don't understand it now, that's fine. We will see more details in unit file. It will be clear. What I mean to say is that accurate capacitance information can be fed back into the power compiler for accurate power analysis. Right? Now we've been talking about switching a lot. We've been saying that switching power depends obviously on switching. But how do we give this information to Power Compiler? How does Power Compiler know? We give it a netlist, we give it a design which has 10,000 gates. How does Power Compiler know that what net switches how many times, or what gate switches how many times? How does it know that? This information can be provided to Power Compiler, or it can be estimated. This type of information is called switching activity, right? So the dynamic component usually accounts for a large. Obviously, the dynamic component is the larger part in the total power consumption as compared to the static component. Internal power of cells and transitions from logic 0 to logic 1 and vice versa will directly affect the dynamic power of the design. This toggling of logic from one value to the other is called the switching activity. Right? Combined together, we call it the switching activity. Now, how is switching activity modeled? Now, there are two very important factors at play here. One is known as the static probability. So, static probability is the probability that a signal is at a specific logic state. Now, please understand that dynamic power is both state and path dependent. So, you should first know, the Power Compiler should first know what state the signal is in. Right? This affects both dynamic power, plus it also affects the leakage power. Right? Because leakage power again is also state dependent. So, it is expressed as a number between 0 and 1. SP1 is the static probability that a signal is at logic 1. Similarly, SP0 is a static probability that the signal is at logic 0. So, how the static probability is calculated? It is calculated as the ratio of time period for which the signal is at certain logic state related to the total simulation time. So, for example, if SP1 is 0.7, it is known that a signal is at logic 1 state 70% of the time. We do not need to know that when the signal is 1. We only need to know, let's say that total simulation time is 1000 nanoseconds. We do not need to know at which point the signal went to 1 or at which point the signal went to 0. We just need to know the total amount of time the signal stays at 1. Right? That's the only thing we want to know for static probability. Second important factor is known as a toggle rate. Toggle rate is a number of toggles a signal makes, a net makes from 0 to 1 and 1 to 0. A net, pin or a port, right? Again, we do not need to know when it went to 1 or when it went to 0. We just need to know the form, right? The number of time it transitions in a given time. That's a toggle rate. So toggle rate is usually per second basis. So toggle rate would be another count divided by the total simulation time. Right? So the file which has this information is called SAIF, switching activity interchange format. So the accuracy of the power calculation depends on the accuracy of switching activity. So what is the best way to calculate switching activity? As I was saying before, for a particular design, again let's take an SSM. We will, in all of the cases, we always have a stimulus, a test bench that is exercised at SSM for real world cases. We take such test case, we run it for, let's say, 1000 nanosecond, 2000 nanosecond, whatever time is suitable. We run it for that. We dump out the waveform using the VCD format, for example. And now the VCD has all the information that we need, right? A VCD, let's say we are running this simulation on a gate level. Right? Now at gate level, for each of the net, the VCD has information when that net toggles. For each of the pin, it has the information that how much time does it stay at 1, how much time does it stay at 0. What we now have to do is just convert the simulation data into the SAIF, right? So SAIF is an ASCII format supported by Synopsys to facilitate the interchange of information between various Synopsys tools. We can use the command called read SAIF to read the SAIF file. We can use the command write SAIF. Write SAIF is not obviously. When you generate SAIF from simulation data, you have to read it in. The write is used for some other purpose. It's used when we use some estimates, we can write out those estimates using write SAIF. Right? So the main purpose is that the main aim is to provide accurate switching activity, and for that we need a good stimulus, right? Good means a mission mode stimulus, a mode which mimics the real world application, right? So we generate the simulation data. So the SIF generation can happen at multiple levels. First, it can happen at RTL level. What is captured? Synthesis invariant element. What does synthesis invariant means? All the registers would be captured, right? The registers are synthesis invariant, right? Or you have used any hard-coded cells, they will be captured. They are synthesis invariant, right? Invariant means they will not change after synthesis. They will stay. All registers inside always drop. Some will be optimized off, obviously, but for SIF purpose, we can say that they will stay, right? What is not captured? Internal nodes are not captured because there is no gate level data, right? So there are no internal nodes. Obviously, correlation of non-synthesis invariant element, there will be a lot of combination logic which will get optimized off. It is not captured. Glitching is not captured, right? Because it doesn't have accurate timing information. State and path dependencies. Since optimization changes the state and path dependencies, right? When you optimize a combination logic, you will change the number of nodes, and hence you will change the state and path dependencies. What is the trade-off? You get a fast runtime at the expense of some accuracy. So the first level SIF 5 can be generated from RTL simulation, right? It will be very fast, but it will be least accurate. The second level can be, so what you could do is you can do a first pass synthesis, and now you can use that gate level netlist to generate a more accurate SIF 5. You can do a zero delay or a unit delay simulation. Now, what is zero delay and unit delay simulation? I hope you will get to learn that in another course, but I just summarize here. The simulation which is done without accurate gate delays, which the unit delay or a zero delay assumes that each combination element has zero delay or unit delay, or each sequential element has zero delay or unit delay. So it does not have an accurate delay information. It assumes a default delay for every case. This kind of simulation is again very fast compared to the accurate delay simulation. But the advantage is that what is captured is that it has all the synthesis elements, right? Because it is a gate level netlist. It has internal nodes, it has path dependencies, it has state dependencies, everything, right? What is not captured? Some path dependencies and glitching. Is all of these, since the delays are not accurate, they are just zero or unit. The glitching is not captured, and obviously some path dependencies are not captured because because again the delay is not accurate, right? When the accurate delay comes into picture, some transitions might change, some transitions might follow some other transitions, so there will be some state, some path dependency which will not be captured. But it is very much more accurate than RTL, but it has a significantly higher runtime. When you go into the industry, you will see that RTL simulations will run the fastest. Gate level simulation with unit delay will run slower. For example, an RTL simulation that runs in, let's say, a couple of hours for a big design will take probably a few more hours for gate level unit delay, and for gate level with accurate delay information, it might even take a couple of days. Right? That's the time, simulation time increases exponentially with the number of elements. RTL has the least number of elements. Gate level netlist has a lot more elements than RTL. Again, gate level with accurate gate delay again has a lot more computation to be done, right? So full timing gate level, what is captured? Everything, highest accuracy. The trade-off is again the high runtime, right? It has a lot more runtime than RTL and gate level. So what is the best trade-off? You do first pass synthesis, you get a gate level netlist, run it through simulation, get the switching activity. Right? That's the best trade-off. So this is the graphical, this is the flowchart. So RTL design, VCSMX is a simulation tool from Synopsys. It can directly dump spec for you, right? Or you can run through simulation. If you use any other tool, you can dump a format called VCD. You can use a utility called VCD to SAIF, This is again from Synopsys Edges. It will dump a SIF file for you. In any case, you need a design SIF file. You can plug back this SIF file. You can use a read SIF inside design compiler, power compiler, and now based on the switching activity, power compiler will give you the power number. It will give you the average power number. You go through gate level design. You synthesize it. Either you can do it. Since you are working at RTL, you will have a slightly lesser accurate SIF. That's fine. It's good for start. It will give the average power numbers. Again, you will go through synthesis. You will do some power optimization maybe. Then you will go to a power reporting tool. Prime time PX is nothing but again a tool which will report power for you. The SAS map is a name mapping which will convert this SAIF into, since the name changes after synthesis, so this utility will map the names of RTL to gate level netlist so that this new SAIF, this name change SAIF can be read inside prime time PX and you can analyze power. What we will see in this session, we will see our scope is this one, where we read the SAIF in design compiler, analyze power, optimize power. Right? This is where we are focusing. This step is again very similar. This step is not too different from this step. The only thing here is that prime time PX you are using after synthesis. You can even use design compiler, power compiler after synthesis. The results are same. The engine is same. The software is same. Right? Now let's see a safe example. This is a safe example. This is a SIF example. It tells what is the design name. Design name is instance is TB. Top level instance is TB. Might be a short form for test bench. It tells what tool is used to write this. Now this instance TB contains two instances, DUT and U12053, something like this. For each of the nets, this file tells us that total simulation time is 99999 nanoseconds. Time scale is 1 nanosecond. Each of these nets, T0 is the amount of time that net stays at 0. T1 is the amount of time that net stays at logic 1. Tx is the amount of time that net stays at logic value x. Tc is the toggle count. You can see the toggle count of each of the nets. This is toggle count is 46. This net toggle count is 0. You can also see that it stays on 0 for 0 time. That's why obviously the toggle count would be 0. It never transitions to 0. It all the time it stays at 1. This net again, the T0 is 61. T1 is something. T1 is not. The toggle count is again 26. Again similar for this instance here. It tells us again T0 T1 value. Again it tells us that it probably has inputs A and B. So it tells us that condition A, when A rises, what is the I think IG is the so it tells us what is the toggle count when in different conditions. Condition A rise, IO path B. Condition A fall, IO path B. B rise, B fall. So it fixes one input, it transitions other input, rise and fall, and then it tells us what is the toggle count, right? So from this SAF file, it will be easier to understand the SAF file if you have a corresponding. If you can take a look at the TB, but I don't have that. What you can do is you can experiment on your own. You will probably know how to do RTL simulation or gate level simulation. Take a small design, take a small test bench, run it for let's say 100 nanoseconds, and you can dump out the SAIF file, right? I'll probably not have this. I'll not probably cover this in the lab, but it's very easy to do this. I'll see if I can find out an SAIF file and read that and then cover this in lab, but I'm not very sure about it. So now this till this point we know what power numbers, what are the different types of power, the static power, the dynamic power, internal power, switching. We know how power compiler reads this data from the standard cell library. We also know how to provide the switching activity information to power compiler. So now we have all the input data that we can give to the tools. Now, how do we analyze power? Right? So it's very simple. We from either gate level simulation or RTL simulation, we generate a switching activity. We give the technology library gate level netlist. So over and above the setup that you do for design compiler for basic synthesis, you just need to have one thing, which is switching activity. Right? That's the only thing you need to have. Rest all things are same, and what we do is we just do a report power. Just like report timing or report area, we do a report power. Report power has these many options. We'll probably see a few of those in the lab. You can read again. You can read the man page. This is the report power report. So it tells us that what is the global operating voltage, this is the VDD. It tells us what are the units. The leakage power unit is picked up directly from the library. The dynamic power unit is derived from B, C, and T units. So this now tells what is the internal power breakdown, the combinational power, sequential power. It tells us what is the count, and not other power, I guess, would be hard macro power. Design does not contain any hard macro. It tells us what is the internal power and the switching power. It tells us that obviously total dynamic power is the sum of internal power and switching power. You can see that here the internal power is much more than the switching power. Right, 76% is the internal power. What this tells us that this tells it is probably a report just after synthesis. Obviously, the number of nets in a pre-gate level design are much less. The real capacitance will only come after post level, right? So the switching power would increase in most of the cases after the layout is done. The internal power would remain same. Why? Because internal power does not depend on external power. And will probably, I think probably because the number of gates, the lot of buffers and inverters will be inserted after layout, that will cause more power. So this is the pre-layout power, right? The post-layout power, dynamic power, or leakage power, both will grow because the number of cells, number of nets, both will grow. Right? It also tells us what is the leakage power. So you see that for this particular design, for this particular technology, the dynamic power is much more than the cell leakage power. In fact, the cell leakage power is kind of negligible, but it is not so in the present technology. The leakage power is a very real threat in designs which are being done in 45 nanometer and below. It tells us the breakdown also, the estimated power, the netlist power and the estimated clock free power. Again, clock free power can only be an estimate at this point because no layout has been done. I'm not very sure how it's able to estimate clock free power. I think it's just calculating the power of the buffers in the clock free network. There won't be so many buffers. That's why we see that it's a lesser component, right, in terms of the total power. So, we summarize: total power is a sum of leakage power and dynamic power. Dynamic power is a sum of net switching power and cell internal power. Now, a good question would be: I do not have any switching activity. I haven't done any simulation. I don't have any switching activity. What do I do? So, power compiler provides some default values. So, power compiler needs to only know how the inputs are switching, right? From each of those inputs, it can know how all the internal nodes are switching, right? So it uses something called P1. It assumes it's 0.01. What it means is that for each of the input, it will assume that the input stays at 1 only for 10% of the time. This is the assumption. This is the default value of the input. So there are two things to switching activity. One is the static probability we're talking about. Other thing is the toggle rate. So for static probability, it assumes to be 0.1, 10%. Static probability for the signal staying at logic level. Toggle rate, it assumes the toggle rate to be 0.1 into FCLP. That means for each data signal, it assumes that the toggle rate is 0.1 into the clock frequency, which is specific to that net, specific to the data signal, not the maximum frequency. Although there is option by which you can control, you can say that okay, assume that all the nets will work at maximum frequency and so on. So CLK is the frequency of the inputs related clock. The command to apply these things is called fetch switching activity. You can use this command to give some default activity values. So using the defaults for static probability and toggle rate can be reasonable for data bus, but it might be unacceptable for some other signals like reset or a test signal. Now reset and test enabled signals, so a signal like reset will toggle very frequently. It will toggle once or twice during the reset sequence, and later it will be stable and deactivated. Such kind of toggle rate values might not be good for the signal. So you should be careful about some signals which might be static for a long amount of time, or some signals which might have a greater activity in it. So these defaults are otherwise good for maximum number of data assets. Right? So default values, these are the variables that define the default values. Power, default, static. So again, static probability, toggle rate. So the variable is power, default, static probability for static probability, power, default, toggle rate for toggle rate. Now you have a variable called power, default, toggle rate type, which tells that the default is fastest clock. That means by default, power compiler will use the fast. So let's say you have multiple clocks in your device. It will use the fastest clock as the value of CLK. You can also change this by applying by using this command fetch switching activity. You can look at the man page and see, and you can apply for each of the signal. You can say that each of the input use a particular clock. So this was what you do when you do not have a switching activity with you. You can apply some default switching activity and calculate the balance clock. So we are done with understanding the power terminologies. We know now how to provide, what to provide to power compiler to analyze power. We saw the report power. Now let's come to some power optimization techniques. Right? So now we know how to report power, but we have to understand now how to optimize power. Right? So clock gating is, I would say, it is the most popular RTL or gate level power optimization technique. Clock gating applies to synchronous load enable registers, which are the group of flip flops that share the same clock. So we are talking about a group of a type of circuit which is very frequent in your. It is very popular type of circuit. It's called shift register type of circuit. It is very popular. I mean, your design will have a number of shift registers which share the same clock and same synchronous control signals that are inferred from same HDL variable. By synchronous control signals, we mean it could be a synchronous load enable, synchronous set, synchronous reset, or synchronous power. Right? These types of registers are conceptually represented by a register with a feedback loop. So they have a feedback loop in place. This feedback loop is activated on an enable signal, right? The enable signal, what we are talking about is the synchronous control signal, the loading signal, for example. If this feedback is enabled, so for some of the state, this feedback would be enabled, and the register, the whole bank of registers will maintain the same value. What it means is that a register bank which maintains the same value cycle after cycle, the data pin is not toggling, but the clock is always toggling. It consumes unnecessary power. Clock gating saves power by eliminating the unnecessary activity on the clock associated with reloading register banks. Right? Sounds complex, but it is very simple when we look at the figure. So let's look at a register bank. This register bank might have 10 registers, 8 registers, 16 registers, any number. But so it has multiple flip flops. Data out goes to a mux, data in goes to a mux. Whenever enable is 1, load enable, a data value is loaded here. Whenever enable is 0, this keeps on cycling with the same value. Right? This enable would be generated from a control logic which is working on the same clock as the register bank. So this is a very typical circuit that is a candidate for clock gating. You will not even realize it, but this is how a lot of code. There are a lot of registers like this. So you have an always block, you have a reset condition, and then you will have an if condition. You say if enable, some enable, data gets new data, otherwise data does not change. So the if enable condition, that if is this part, if en. This en would probably be generated from a control logic working on the same block. So a lot of RTL code is like this, which results into a shift register which has a feedback mechanism into play. This is a perfect candidate for clock gating. Now, what the idea is that we want to, for the part where it is not enabled, where enable is 0, we want to switch off this clock. We want to make this clock 0. We don't want togglings on this clock. This will save power. This will save the dynamic power, not the leakage power. Now let's look at the modified circuit with the clock gating in place. This is called latch-based clock gating. There is a type of clock gating which does not involve a latch. So let's, before even looking at this figure, let's focus on what is clock gating. How we can switch off the clock. So we can, very popular method is AND the clock with an enable signal. So clock ANDing it with an enable signal. If the enable is 0, the output will be 0. If the enable is 1, the output will be clock. So this is called AND type of clock gating. You can have an OR type of clock gating. If the enable is 1, the output is always 1. Whereas the enable is 0, the output is nothing but the clock input. Right? So a clock combined with an enable signal, both fed into an AND gate or an OR gate, will result into some kind of clock gating. Now, AND gate is popular for the clock, the type where the active clock edge is the positive edge trigger. What it means is that if the clock is high, so the enable signal should not toggle. Ideally, the enable signal should not toggle when the clock is high. What it means is that if the enable signal toggles when clock is high, let's say it goes from 1 to 0, right? The clock edge will be clipped off. You do not want that. So for such type of AND gating without latch, when you do not use a latch, you can draw it on a paper and see that without using a latch, the AND gate and OR gate both, now the enable signal is free to toggle at any time, right? So you have lot more restrictions on EN, the enable signal. If they toggle during unnecessary time, the clock edge can get clipped off. We do not want that. We do not want that. So that is why we use a latch. So for a particular type of clock gating, we use a particular type of latch. Now let's look at this figure now. In this case, the clocks are positive edge trigger, and now we want to use an AND type of gating. So this is where the gating takes place. This is the gating cell. So enable signal and clock are gated to provide an EN clock. Now the mux at the data input is removed. The enable signal, instead of going to a mux, goes to a latch. The clock goes to a latch. Now latch is transparent at the falling edge. Latch is of the opposite polarity of the flip flop. Now what it does is that, so here we have waveforms of clock and clock invert. Now let's say enable toggles when clock is high. If enable toggles when clock is high, this latch does not pass this value because this latch is closed when clock is high. When clock is low, this latch is transparent. So ENL value will get updated after clock falls sometime after that. So this is the trigger event for ENL rising. Right? The value of EN gets passed on to ENL. Now ENL is gated, is ANDed with clock. So now since clock is low, EN clock remains low. Next high edge comes here. Right? This is the trigger form. What it tells us that whenever EN goes high, if the clock is high, there is no effect. The next clock edge will be transferred. if the latch was not there, assume the latch was not there, EN will directly go to ENL. What this will do, it will create a false edge here. It will create a half edge here. This would be the waveform, and you do not want that. You want the full width of the clock cycle of the high pulse, right? You want the full high pulse, not the half high pulse or 10% high pulse. It is dangerous, right? So latch will prevent this. So latch, this is the actual gating circuit, the AND gate. The latch simply makes sure that EN does not transition when clock is high, right? So that the edge is not flipped off, and it provides a stable full pulse of the clock whenever there is an enable. So this circuit, it does two things. First, it gates off the clock when it is not enabled. It is same, the functionality is same here. This data, this register bank gets the same data whenever enable is low. Here, this data is stable when enable is low because there is no clock, so data is stable, there is no cobbling here. Further, the second thing that latch does is it gives us a very stable circuit to avoid glitches on the clock, right? So latch is to avoid glitch, and gate is to actually gate the clock. What is the drawback? It adds one latch and one AND gate. It gets rid of the mux. So it adds, let's say, one latch extra, assuming mux is equivalent to AND gate in terms of area. It will add one latch per register bank. So it results into an increase in area, but gives us a lot more advantage in terms of power, right? And if you have bigger register bank, so you have one latch per register bank. If you have lot of bigger register bank, the area growth is negligible, but the power saving is good, right? The dynamic power saving. So it's a very important power saving technique. And in my number of years in the industry, I have used it every single time, every one of the time, right? So how do we insert this type of clock gating? Two methods. We saw the gate clock option in compile ultra, it does that. So compile ultra minus gate clock will add clock gating. So you don't need to keep doing the RTL, right? So compile ultra minus gate clock will add this in the either the RTL, or you can even add it in the netlist using compile ultra minus gate clock. You can read the netlist, already synthesized netlist. You can say compile ultra minus gate clock, and compile ultra will do that for you. There's one more command called insert clock gating, but it only does that at the RTL stage, right? So the preferable command to use is compile ultra minus gate clock. Although both of them do the same thing, but insert clock gating cannot do it on an existing synthesized design, right? Now there are a lot of clock gating styles. So the diagram we saw was the clock gating style for positive edge trigger logic, right? The cell used was latch plus an AND gate. So there are a lot of styles like that of clock gating cells. The command to specify these styles is called set clock gating style. If we do not apply any style, these are the default settings that we will use. So these are options that go along with the set clock gating style command. Sequential cell type is latch. Minimum bit width for a register bank. So is 3. What it means is that any register bank which is, so it is not useful to add clock gating for shallow register banks. That means if let's say register bank is only 2 registers, right? So you will add one latch per 2 registers, the area increase will be very significant. So you want to exclude all registers which are less than some threshold. You can play with the threshold. You can play with the numbers and see how much is the clock gating percentage, how many clock gates are added, what is the area increase. You can do some experiment, but default value is 3. That means for all register banks, now that register bank should follow some guidelines, right? Should have a particular kind of structure, that is the feedback loop and so on, right? And an enable condition and so on. So all such register banks which meet the criteria wider than 3, wider and including 3, will be candidate for clock gating insertion. Let's not go into setup constraint, hold constraint. We'll talk about it later in unit 5. Positive edge logic is AND. That means for positive edge triggered flip flop, it will use an AND type of gating. For negative edge triggered logic, it will use an OR type of gating. You can draw it on paper why AND gate is suitable for positive edge triggered, why OR gate is suitable for negative edge triggered. Right? It's very easy to use. Control point control signals are related to DFT because you want when you want to test the design for manufacturing defects. That means in scan mode, all these latches should be transparent. So you have a control point and a control signal name. Again, observation point and observation logic depth are related to scan. Maximum fan out, number of stages, 1. Sharing means that do you want to share this clock gate with any other register point? It is false, by default it's false. Now let's talk about integrated clock gating. What it means is that this is the most popular form of clock. I mean, we have discussed clock gating, but now almost all technology library vendors, what they do is that they make. So what they do is they will create one standard cell out of this latch plus AND gate. So there will be only one standard cell internally which has a latch and an AND gate, and it will have the inputs like clock, enable, and output, right? And some inputs and outputs for scanning. This type of cell is called ICG, integrated clock gating cell, right? That's what we are talking about here. So how do we use that? This is the most popular form of inserting clock gates. That means by applying an integrated clock gating cell. So how do we do that? We say that set clock gating style. We tell, so there will be multiple ICG, multiple integrated clock gating cells. One will be for positive edge triggered logic, one will be for negative edge triggered logic. So we tell design compiler that, or power compiler, set clock gating style. What kind of cell I want to use for positive edge triggered logic? What kind of cell I want to use for negative edge triggered logic? This is one example of this command. Set clock gating style minus positive edge logic integrated. This is the library name, and this is the cell name. So we are telling by this command, by issuing this command, we are telling our compiler that for clock gating, for positive edge triggered logic, from the library integrated, use my cell, right? For clock gating cells also in the library there will be multiple drives available. So you can choose any drive, and that cell will be upsized or down, maybe later to solve the DRC solutions, right? So this is the way. This is the clock gating. This is the way you can use compile ultra minus gate clock to insert clock gating. Before that, before doing compile ultra minus gate clock, use the set clock gating style command to tell design compiler that use this particular type of library cell for clock gating. You can also use a command called after synthesis. You can use a command called report clock gating. These are two different report clock gating commands. One is the summary, one is the more verbose report. So this is a very interesting statistic that it will tell. So it tells us that for this particular design, number of gated registers are 66.67%. That means, okay, this has only 4 and 2, only 6 registers. Let's look at a slightly more. Okay, this doesn't have a detail, but we'll have what we'll do is in the lab we will insert a clock, the clock gating on a design and see what is the percentages of the. In my experience, for bigger designs, I have seen about 80% of the registers which qualify for clock gating. What it means is that in a bigger design, it can happen that about 80% of the registers fall in the category of shift registers with feedback mechanism. It's a very common circuit. You can see that. You can, when you code, you won't even know it, and it will be a shift register with an enable pin, which controls the feedback. So this is why clock gating is becoming so popular. It gives so much gain in terms of power saving, and the area increases not that much. So what it tells the report clock gating, it tells us how many number of clock gating elements is added. It added only 1. Number of gated registers is 4. Number of ungated registers is 2. Total number of registers is 6. On the right hand side, the report is more verbose. It tells us that there are 3 clock gates, clock gatings which conform to clock gating style 1. What is that style? Sequential cell is latch, minimum bit width is 2. I am not sure what enhanced min bit width means. Positive, this is the integrated cell that is using from the library. Negative S logic is OR. Control point is before. Control signal is scan enable. It is related to DFT. Let's not go into that. Number of stages is 2. These are the clock gates. So it told us there are 3 clock gates. These are the 3 clock gates that is inserted. This is the summary again, very similar to the left hand side summary. So it tells us that 100% of registers are gated. In the lab, we'll also see we'll see report clock gating. We'll use compile ultra minus gate clock. We'll also look at the netlist and look at the clock gating structure. It will become much more clearer then. Right? If it's not clear now, you should also try this in the lab. Now the last step. So now in this last session we were focusing on the power optimization technique. So one thing you should do always is use the clock gating option if your library supports an integrated clock gating. Even if your library does not support an integrated clock gating, now you know that any positive S triggered logic, the clock gating cell, a good clock gating cell would be a latch plus an AND gate. You can without using an integrated clock gating cell, you can tell DC that by using set clock gating style that so if you're not using ICG, DC will add a latch and an AND gate itself. So it is not compulsory to use ICG. You can choose not to use it, and then DC will add a latch and an AND gate by itself, 2 separate cells from the standard library. But first thing you should check in your library if the ICG is available. If the ICG is available, please use that. It gives lot more advantage later in the field. Later, when you want to do anything, you want to set some special constraints, or you want to do any optimization, separate optimization. The presence of ICG will help a lot because now you have one particular type of cell. You know that this is a cell that is used for clock gating, and you can use some scripts, some typical scripts to extract those cells and do things on it. Right? So it always helps to use ICG. So the first principle, you should always look into the library and choose and see if the ICG is available. Right? Now, now this was a very particular technique, a very special technique to save dynamic power, which we can use as part of compile ultra. Right? Now let's look at the other power optimization things available inside DC. We have seen this flow where we provide libraries, netlists, and optional switching activity. When I say optional, I mean that you can also choose to use the set switching activity command to set the default switching activity if you do not have SOS available. Right? Now there are power options. We will see what these options are, and now DC will perform power optimization in addition to timing and area optimization, and you have a power optimized gate level network. For leakage, what power compiler could do? Power compiler will, for leakage, also for dynamic, for both it's true that power compiler will reduce power consumption on paths with positive timing slack. Enabling power optimization does not change the cost priorities of paths. It will just add one more constraint. What it tells us that power can only be optimized whenever timing slack is available. So for critical paths with very fast clock frequencies with no positive slack, it is not possible to do power optimization. Any power optimization build step will try and replace a faster cell by a slower cell, and a slower cell will not help in case the path is critical. So any critical path with fast frequency will restrict power optimization. Right? When the target libraries are when you have leakage power attributes available, and when you have cells with multiple threshold voltages, power compiler will use the library cells with appropriate threshold voltage to reduce the leakage power. For example, you have a high VT, a standard VT, and a low VT. We call them HVT, SVT, LVT. What power compiler will do? It will choose HVT cells for all the non-critical paths. This will reduce the leakage power. For dynamic power optimization, it needs a switching activity. You can either provide SAIF or apply some default switching activity. Again, for dynamic power, you know that same kind of, let's say for HVT cell will have lower dynamic power as compared to LVT cell. if the HVT, so it will choose not even VT dependent. Okay, VT will become VT dependent, but there will be some cells, let's say some flavor of AND gate, which will be which will eat up lower power, lower dynamic power when compared to some other. For example, gate with higher capacitance at load will consume more switching power. So there are a number of gates available. You have all the switching power information available. Now what DC will do? It will try and optimize dynamic power by using gates which have low load on the output to reduce the switching activity. What this will do is that it will slow down your power again. Right? Now let's say you have let's say you have a 4-input NAND gate. Now a 4-input NAND gate might be very good for finding when compared to multiple stages of 4-input NAND gate. Let's say 3 stages. So you will compare a 4-input NAND gate with, let's say, 3 stages of 2-input NAND gate, or let's say 2 stages of 2-input NAND gate. So a 4-input NAND gate will probably be better in area, but it will eat up more power. So what DC will try to do is it will replace that multi-input gate, heavy gate, by a multi-stage network. What this will do, it will make the path slower but reduce power. If it makes the path slower, this cannot be applied onto critical path, right? So and it obviously, if the switching activity is accurate, it will help DC to analyze state and path dependencies in a better way. So dynamic power optimization requires switching activity. Bottom line, again, it will only happen for non-critical paths. So how do we annotate switching activity? We say we need SAIF and we can annotate the switching activity, or if we do not have SAIF, we can use set switching activity command to set the values, default values, right? How do we enable power optimization? For power optimization to work best, the library should support multi-VT cells, especially for leakage power. Yeah, so sorry, there are these two sides of the term. So enable leakage and dynamic power optimization. We have to use these. We can use these commands before compile. Please note, before compile you have to do that. Set leakage optimization to true. Set dynamic optimization to true. By default, I am guessing they are set to false. What it means is that by default, compile will not do any power optimization unless and until you set the variables to true. Right. So this is actually the summary part. For power optimization to work best, especially for leakage power, the library should support multi-VT cell. If your library does not have any multi-VT cell, if your library for all the cells there is only one VT type, let's say you only have standard VT, it's not much useful for power optimization because design compiler does not have any choice. So there is no use, in fact, in even enabling power optimization. The results will not be much different. So to use the power of leakage power optimization, you should have multi-VT cells. So any good library for deep submicron technology will have cells with different VT cells, right? I'll check if the library we are using has multi-VT cells. If not, then we cannot do many things in the lab, right? Chips for handheld applications, they save power. So now there's a technique. These are very basic techniques to reduce power. That means using high VT for non-critical power, using clock gating. But consider a smartphone. Now a smartphone, consider a chip, a very complex chip that is the brain behind a smartphone. So what components it will have? It will have a baseband processor. It will have an application processor. So application processor is usually what we see in the specification as denoted by quad core or dual core, small core, and so on. So this is application processor. There will be again a baseband which will decode the terrestrial the signal, the GSM signal or the CDMA signal. Then there will be a lot of cores which will do different jobs. One core will do the job of video processing. It will probably have a separate GPU for that. One core will do the audio processing. One will be a touchscreen controller, for example. So there are so many components. In the smartphone is a very complex device. There are so many components doing so many different jobs. Now consider that you are talking on phone. When you are talking on phone, your video processor part is not playing any role. So what such complex chips try to do is that they implement different voltage arms. What they do is different parts of the chip works on different voltages. Even if they are working on same voltages, they have different supplies, so that one part can be switched off when not in use. This saves a lot of power. What if your video encoder or video decoder is on even when you're talking on phone? Unnecessarily power is being consumed. These types of flows are called low power design flows. Synopsys UPF is one such flow. Unified power format is one such flow which helps us in implementing these types of chips. It's a the understanding, the explanation of this flow is outside the scope of this course, so will not detail that. But please understand that I want to stress on this point that please understand that clock gating, leakage power optimization, dynamic power optimization, all these techniques are basic power optimization techniques that you can use for a single voltage design, right? So whatever designs you do in the lab, in your lab will be single voltage design. You can go back to design compiler if you have the power compiler feature available to you. You can see your library. You can first understand. The first assignment is look at the library, understand how the power numbers are represented. Second, try and insert clock gating. You don't have to do anything special in your RTL. Just use the set clock gating style and compile alpha minus break clock. These two things. Third thing, use these two switches to enable the leakage and dynamic power optimization by setting the default switching activity. See the report power report. Next step would be in one of your simulation. You must be doing some kind of simulation in some design in any other course. Dump out the VCD, generate an SAIF, read back the SAIF in design compiler, report power, do a report power. You should do all these things to understand the concept better. Right? Thank you.